Welcome back. I'm Muggsy, and today I'm going to explain how to balance a chemical equation. Up here we see a chemical equation, and like all chemical equations, this represents a specific chemical reaction. Our reactants, hydrogen gas and oxygen gas, react together to produce water vapor or steam. This is the combustion of hydrogen in the presence of oxygen, like what happened when the Hindenburg went down. There is a problem with this chemical reaction though, and that is we are violating the first law of thermodynamics. Now, you may recall, or you might not recall, the first law of thermodynamics is that matter and energy can neither be created nor destroyed. You can't get something out of nothing, and you can't take something and turn it into nothing. Everything in the world comes from somewhere and goes from somewhere. So for instance, if you take a piece of wood and you burn it up, that wood didn't just disappear. The molecules from the wood went into the atmosphere as carbon dioxide and water, and some of the molecules are left behind as ash. And if you collected all the CO2 and water in a big balloon, and you collected all the ash, and you put that on a scale, and you measured it against the initial mass of the wood and the oxygen that was burned along with the wood, those two sides would be equal. And so, our reactants in a chemical reaction must always be equal to our products. And so let's begin by just kind of counting up how many hydrogen and oxygens are present in our reactants and products. And the way I like to do this is I basically make a table, reactants on one side and products on the other. And then I go through and look at each individual element and inventory them. So hydrogen, in my reactants, there's 2 of them. And in my products, there's 2 of them. So far, so good. Oxygen, in my reactants, there's 2 of them, O2. And in my products, O. There's 1 of them. So this chemical equation, the way I have it written out, is violating the first law of thermodynamics. Our hydrogens are fine, but it looks like I'm just making oxygen disappear and go off into space and be gone forever. And that's not possible in the world that we live in. It violates the first law of thermodynamics, sometimes known as the law of conservation of matter and energy. So we have to use coefficients to change the whole number of molecules to make it so that we have the exact same number of atoms in our reactants that we have in our products. So I need to get 2 oxygens in my products to match the 2 oxygens I have in my reactants. So I could just put a little 2 right there, right? No, of course not. If I put a little 2 there, I'm actually changing the whole reaction. I'm not combusting hydrogen and oxygen to make water, I'm combusting hydrogen and oxygen to make hydrogen peroxide. It's something totally different. So you can't just go around messing with the chemical formulas of what's in your reaction. What you could do though is say instead of 1 water molecule is produced, I could say 2 water molecules are produced. And then I would basically have to recount everything. So if I had 2 H2Os, I'm now gonna have 2 O's, which is great. That's exactly what I need. They're balanced in the reactants and the products. The problem is I also have 2 times 2, 4 hydrogens in my products. And that's not good because I only have 2 hydrogens in my reactants. So again, it looks like I'm violating the first law of thermodynamics again. Fortunately, I could just, instead of having 1 hydrogen molecule, I could have 2 hydrogen molecules in my reactants, and then I would have 2 times 2, 4 hydrogens in my reactants, and now all of a sudden my reaction is balanced. I've balanced this chemical equation because I have 4 hydrogens in my reactants, and I have 4 hydrogens in my products, and I have 2 oxygens in my reactants and 2 oxygens in my products. So I'm not breaking the rules of thermodynamics. So We balance chemical equations by changing these coefficients in front of the compounds and molecules that we have. We can't go around and just monkey with the actual chemical formulas of what we have. I couldn't make this O3, for example, because those chemical formulas are accurately representing what's actually going on in the reaction. We're just changing how many of them there are. And then we learn some kind of interesting stuff. So it's not just one molecule of hydrogen reacting with one molecule of oxygen. You actually need 2 hydrogens to every 1 oxygen. And that is called the mole ratio. For instance, if I wanted to get 2 moles of water, you could basically think of this as a recipe. I would take 2 moles of hydrogen and react it with 1 mole of oxygen, and I would get 2 moles of water. The ratio of hydrogens to oxygens in my reactants is 2 to 1. Or you could say the ratio of oxygens to hydrogens is 1 to 2. Now, why did I say 1? Well, you know that if there's no number in front of a molecular compound, that number is actually 1. We don't draw it. We don't need to. It's just like x in algebra class. You wouldn't say 1x, you would just say x. So I wouldn't say 1O2, I would just say O2. If there is more than 1, you do absolutely need that coefficient in front. So if it's 2x, you would have to write 2x. Just like if it's 2 H2s, you would put this 2 coefficient in front. Okay, that was a lot, but hopefully you're starting to understand how to balance these chemical equations and why that's important. We're going to do a lot of more examples until you really understand it. Okay, let's look at another example. We have the reaction of lithium metal with aqueous aluminum bromide to produce aqueous lithium bromide and aluminum metal. Now again, we would want to start to check and see if this equation is already balanced, and we do that by inventorying what we have in the reactants and the products. And we just go element by element. So let's start with aluminum. And here there's no subscript after it, so that means we just have 1 in our reactants, and looks like we just have 1 in our product as well. For our bromine, Br3, that means we have 3 of them in our reactants. LiBr, there's no number after it, so that just means we just have 1 of them in our products. That's going to be a problem. And then finally, our lithium. Here we just have 1 in our reactants, and here we just have 1 in our products. Well, that's fine. So our aluminums are balanced, 1 and 1. Our lithiums are balanced, 1 and 1. The bromines are going to be an issue. We have 3 here in our reactants and 3 in our products. So the easiest way to balance this is just, instead of making 1 lithium bromide, let's make 3 of them, because now we'll have 3 times 1, 3 bromines. Now sometimes in the process of balancing one thing, you'll unbalance something else. That's okay, just keep working through the process. You should be fine. So we have 3 bromines now, but we also unfortunately made 3 lithiums. So if we have 3 lithiums in our products, but only 1 in our reactant, we're going to need 3 of them in our reactants. So let's put a 3 in front of the lithium there. And now with the addition of those 3 lithium atoms, we're balanced. We have 1 aluminum in our reactants, 1 in our products, 3 bromines in our reactants, 3 in our products, 3 lithiums in our reactants, and 3 lithiums in our products. So just keep adding those coefficients back and forth until you get it balanced. I would really, really recommend you don't skip actually writing out this table of everything in your reactants and products. It's a really good way to catch yourself if you're making a simple mistake. Yeah, you could probably do something like this in your head, but the problems are going to get more and more complicated. And having this table where you actually write all your work down is really going to help you stay organized and make sure you get the right answer, especially if you're doing something high stakes like taking a test. So I really recommend you write this table down just like I'm doing for these problems. Let's look at another example. Okay, here we have an acid-base reaction where hydrochloric acid reacts with magnesium hydroxide to produce water and then also magnesium chloride. Let's make sure that this equation is balanced by inventorying our elements. Reactants on this side, products on this side. We'll start with our hydrogens. 1 in the reactants, 2 in the products. Chlorines, 1 in the reactants, 2 in the products. By the way, when I'm doing this list, make sure all your elements kind of line up across. So if you have H and then Cl and then Mg and whatever here, make sure you're doing the same thing here. Okay, then I'm looking at magnesium. I've got 1 here in my reactants, and I've got 1 in my products. And then I've got oxygen. I've got 2 of them here, because remember, this 2 goes to the O and the H in my reactants. And I have only the 1 in my products. And I see that I kind of made a mistake. You'll notice with my hydrogens, I have 2 here in my products. And I said I have 1 in my reactants, but I don't actually have 1 in my reactants, because in this case, and with some chemical reactions, hydrogen might be in more than one compound. So we do have 1 hydrogen here in our HCl, but we also have 2 hydrogens here in our magnesium hydroxide. So our hydrogens are actually equal to 3. So make sure you're looking for every last hydrogen when you're looking at hydrogen, or oxygen when you're looking at oxygen, that sort of thing. Okay, let's look for what's balanced and what's not balanced. Looks like our magnesiums are balanced, but everything else is not balanced. So let's start with our chlorines, I guess. I've got 1 chlorine here in my reactants, 2 in the products. So it should be pretty easy if I just put a 2 in front of that HCl. I now have 2 chlorines, which are balanced, but I also increased my number of hydrogens. So I now have 2 hydrogens here, plus 2 hydrogens here, for a total of 4 hydrogens in my products. I only have, I'm sorry, my reactants. Did I say products? Reactants. I only have 2 hydrogens in my products, and I need to get 4. So if I put a 2 in front of that water, I'm gonna have 2 times 2, 4 hydrogens, which is gonna be balanced. But I've also upset my number of oxygens, because 2 times 2 is 4 oxygens, but I also have 2 times 1, I'm sorry, 2 times 2 is 4 hydrogens, but I also have 2 times 1, 2 oxygens. And oh, looks like I'm done. 4, 4, 2, 2, 1, 1, 0, 0. So everything's balanced on both sides. So if I were to speak this chemical equation aloud, I would say 2 hydrochloric acids react with 1 magnesium hydroxide to produce 2 water molecules and 1 magnesium chloride. Easy. Let's do some harder problems. Do you remember photosynthesis? Photosynthesis is the chemical reaction that takes place within plants and other photosynthetic organisms, where they take in carbon dioxide and they take in water. And they make, what do plants breathe out? Oxygen. And then one other thing, glucose. That's probably aqueous, actually. That's gaseous. Okay, and because plants take in CO2, the stuff we breathe, and they give us oxygen, the stuff we need, that sustains us as animals. They also give us glucose, which is a great source of food to us. We get almost all of our energy from this glucose produced by plants, either by eating the plants directly or by eating the animals who ate the plants. All right. Next thing to do would be check and see if this reaction, photosynthesis, is balanced. So we got our reactants on one side, our products on the other. I see carbon over here in my reactants, and I only have 1. In my products, I've got 6 of those suckers. Oxygen over here in my reactants, it looks like I have 2. Be careful, I also have 1 here. So 2 in my carbon dioxide and 1 in my water for a total of 3 oxygens. Same thing over here, I have 2 oxygens in my O2, but I also have 6 in my glucose for a total of 8 oxygens. And then my hydrogens, I have 2 in my reactants, and I have 12 in my products. That's a big difference. Okay, now it doesn't actually matter which one of these I choose to start balancing. So we could just start at the top with the carbons. It doesn't matter, any of them will give me the right answer. The cool thing about balancing chemical equations is there are so many different ways you can attack these problems, and as long as you're making sure that your answer is correct and simplified, you're going to get the right answer. So don't stress too much about whether you should start by balancing your carbons or your oxygens or your hydrogens. Let's just start with those carbons. So if I have 1 here and 6 here, I'm going to need 6 times 1 for a total of 6 in my reactant. So let's put a 6 coefficient in front of my carbons. Now I have 6 times 1, 6 carbons in my reactants. But I've also upset my oxygens, right? Because now I have 6 times 2, which is 12 oxygens, plus 1 for a total of 13. Okay, let's mess around. Oxygens are going to be a little bit tough. Let's do our hydrogens next. So I have 12 in my reactants. I have 2 in my products. How many groups of 2 do I need to get 12? Well, that's just a simple math problem. I'm going to need 6 groups of 2 to get 12. So 6 times 2 is going to give me 12 hydrogens, which is perfect. Of course, I've also upset my oxygens now. So I've got 6 times 2, 12 oxygens here, plus another 6 here. 6 plus 12 is 18 oxygens. Okay, so now my carbons are balanced, my hydrogens are balanced, but I need more oxygens in my products. Specifically, how many oxygens do I need? Well, I need a total of 18, and I already have 8. Here's where things could get a little bit more complicated. What I would do is I have 18 oxygens over here on this side, right, in my reactants. And I'm going to update my oxygens by updating this coefficient in front of my O2. But that's not my only source of oxygen here in my reactants. I also have these 6 here. So what I'm going to do is I'm going to take my 18 oxygens that I need to get, and I'm going to subtract the 6 that I'm always going to have from this glucose molecule. And I'm going to get this new number, 12. So 12 is the number of oxygens I need here that, in addition to this 6, will give me 18, which I want to get. So how many groups of 2 do I need to get 12? I'm going to need 6 groups of 2. So I'll put a 6 in front of that O2. And now I have 6 times 2 for a total of 12. Plus 6 for a total of 18. And now everything's nice and balanced. Now, there is a possibility that while you're doing this problem, that you might have gone a little bit overboard. Like, let's say I put a 2 in front of this glucose here. And I have a 12 in front of this CO2 to balance that out. Let's re-inventory everything really quick. Okay, so if I have a 2 here, that's going to give me 12 carbons here in my products. And if I have a 12 here, that's going to give me 12 carbons in my reactants. That's cool. Oxygens, I have 12 here, times 2, which is a total of 24, plus 1 for a total of 25. Oof, that's a big number. And then here I have 2 times 6, which is 12, plus 2, a total of 14. And then hydrogens, here in my reactants, I only have 2. And here in my products, I have 24. Okay, let's just keep going. So we're just attacking this problem in a different way. I'm going to need to balance out these hydrogens, and that's actually going to be pretty easy. So in order to get 24, how many groups of 2 am I going to need? I'm going to need 12 of those. So let's put a 12 in front of that. And so now I have 12 times 2, 24 hydrogens here in my products. I'm sorry, reactants, to balance the 24 that I have in my products. But now I have a huge number of oxygens. So I have 12 times 2, which is 24, plus 12 times 1 for a total of 36 oxygens. Oof, that's a lot of oxygens. Okay, well actually I think I can do that because here in my glucose, I have 2 times 6, which is 12 oxygens, right? So I need to get 36, but I already have 12 accounted for here. So that leaves 24. So I only need to get 24 oxygens here to balance out my products. So how many groups of 2 are going to give me 24? Well, that's 12. 12 times 2 is 24. So now I have 24 oxygens plus 12 for a total of 36. And everything is balanced. But this is not the right answer. I repeat, even though that this chemical formula is balanced, this isn't the right answer. You should always check your coefficients when you're done balancing to make sure you can't simplify it any further. And it looks to me like 12, 12, 12, and 2 are all divisible by the same number. Do you know what it is? It's 2, right? 12 divided by 2 is 6. 12 divided by 2 is 6. 12 divided by 2 is 6. And 2 divided by 2 is 1. And so whenever you can simplify your coefficients, if they're all divisible by a common factor, you should do so, and then you'll get the right answer. And so now we end up at the answer we got earlier with these 3 6s in front. And we end up with
6 carbons here, 6 carbons here. How many oxygen? Well, I'll do oxygens last. 6 times 2, 12 hydrogens here. 6 times 2, 12 hydrogens here. And then 6 times 2, 12, plus 6, 18 oxygens here, and 18 oxygens here. Okay.
So for some of these problems, depending on how you attack them, you might end up with like really big coefficients here. Check to see if they're all divisible by a common factor, and if they are, divide them by that common factor until you can't do that anymore, and then you'll have your final answer. Now, how do I know this is my final answer? Because 6, 6, 6, and 1 are not divisible by any factor other than 1, and dividing them all by 1 is just going to give me the same answer, so I'm simplifying. Okay, here's another reaction for us to balance. Ammonium phosphate plus magnesium chloride makes ammonium chloride and solid magnesium phosphate. So, as with all of our problems, we're going to make an inventory of our reactants and products, and we're just going to go through one by one and count them up. So let's start with nitrogen. Now it looks like I have 1 nitrogen, but we're forgetting that we have this 3 outside the parentheses, which is going to get distributed to that 1. So we're going to have 3 nitrogens. 3 ammoniums contain 3 nitrogens. In our products, I don't see any of that stuff, so it's just 1 nitrogen. Next down, let's look at our hydrogens. Here we have 4, but they're also being multiplied by this 3 outside the parentheses, so that's 4 times 3, 12 hydrogens. Look to see if there's any more hydrogens. No. Here in our products, 4, and then we're not multiplying it by anything, so that's just 4. Phosphorus, I only see the 1. In our reactants, and here I see 1 times 2 for a total of 2. Oxygen, O4, 4 in our reactants. Here, 4 times 2 for a total of 8 in our products. And then I'm kind of running out of space. Magnesium and chlorine. 1 magnesium in my reactants, 3 magnesiums in my products. And then finally, chlorine, Cl2, 2 chlorines in my reactants, 1 chlorine in my products. Now again, as I've said with all these problems, once you've inventoried your elements, it doesn't really matter where you start. There are maybe some kind of logical moves you could do. For instance, it's probably better to start with something that simplifies, that balances really easily. But other than that, just go nuts. So what I mean by that is, here I have Mg3, 3 magnesiums, and here I have 1 magnesium. So it seems to me that that magnesium would balance pretty easily if I just put a little 3 in front, right? That's going to give me 3 magnesiums here in my reactants. And it's also going to give me 3 times 2, 6 chlorines. Okay, now let's balance those chlorines. So I have 6 in my reactants. I need to have 6 in my products. Right now I only have 1, but I could easily have 6 if I just put a 3 in front there. And now I'm sorry, did I say a 3? Oh, I don't know what's going on with my brain. If I want 6 chlorines, I'm going to need a 6 in front. There we go. And that's going to give me 6 chlorines, which is going to balance out my 6 chlorines there. But you'll notice I also changed a lot of other stuff. That's also going to change my number of nitrogens and my number of hydrogens. So let's count those. So 6 times 1 gives me 6 nitrogens now in my products. And 6 times 4 gives me 24 hydrogens. Okay, so now what's not balanced? I see I've got 3 nitrogens in my reactants and 3 in my products. I'm sorry, 6 in my products. So if I have 3 nitrogens for every 1 ammonium phosphate, how many ammonium phosphates am I going to need to get 6 nitrogens? Well, that's just 2. Each one of these ammonium phosphates contains 3 nitrogens, so 2 ammonium phosphates will contain 6 nitrogens. Now that balances my nitrogens, but it's also going to mess with a bunch of other stuff. My hydrogens, my phosphoruses, and my oxygens. So let's count those now. Hydrogens, 4 times 3 is 12, but now I have 2 of them, so 12 times 2 is 24. Okay, that looks good because I have 24 in my products. Phosphorus, I have 1 of them, times 2, that's 2. Okay, looking pretty good because I also have 2 in my products. And then oxygens, I've got 4 of them, 4 times 2 is 8. Hey, perfect, because I also have 8 here in my products. So now everything's balanced. Nitrogen, 6, 6. Magnesium, 3, 3. Chlorine, 6, 6. Hydrogen, 24, 24. Phosphorus, 2, 2. And oxygen, 8, 8. So my reactants and products are totally balanced. The last thing to do here would be to check and make sure I can't simplify this any further. Since there's no coefficient here, and we know that no coefficient basically means a 1, that means I can't simplify this any further. So this is good. 2, 3, 6, and 1. The lowest common factor of all those numbers is 1, so it's balanced and simplified. Perfect. Let's do another. Okay, let's balance this chemical reaction. The combustion of butane. Butane is a fuel with the chemical formula C4H10. And it doesn't just burn all by itself. Like all combustion reactions, it needs access to oxygen. Both of these are gases. The butane, while it's in the lighter, is a liquid, but it gets converted to a gas as it burns. And every combustion reaction, every flame burning produces carbon dioxide. And the one everyone forgets is they also produce water vapor. Okay. So this is the chemical equation for the reaction you just saw when I used my lighter there. Let's do what we always do and check it out to see if it's balanced. Reactants, products, let's go through one by one and see what we got. So it looks like we got 2 oxygens here in our reactants, and we've got 2 oxygens here, but also 1 here for a total of 3 oxygens in our products. We have 4 carbons in our reactants. And we have 1 carbon in our products. And we've got 10 hydrogens in our reactants. And we've got 2 hydrogens in our products. Okay, it doesn't matter where you start. We could do the oxygens first, although it's not going to work easily because if I put a little 2 here, I would have 4 oxygens, but that wouldn't equal 3. So maybe oxygens isn't the best place to start. Let's start with our carbons. We have 4 in our reactants. We only have 1 in our products, so if we put a 4 there, we're going to have 4, which is exactly how many we want. But we're also going to mess with our oxygens. So 4 times 2 is 8. And 8 plus 1 is 9 for our oxygens now. So those are off. Let's take a look at our hydrogens. Here we have 10, and here we have 2. So how many groups of 2 do we need to get 10? We're going to need 5. So if we put a 5 in front of that H2O, that's going to give us 10 hydrogens, but it's also going to give us 5 more oxygens. So if we have 5 oxygens here and 8 oxygens here, that's 13 oxygens. I don't like to see 13. That's kind of a, prime number, kind of hard to divide and figure out. So we've kind of reached an impasse, because check this out. How many O2s will give me 13? Well, I guess you could say 6.5, but you can't have a fraction of something that we have here in our chemical formula. Because you can't have half an O2, that would just be a free oxygen, which isn't part of the chemical formula. So there's no number we can put here to balance this chemical equation. So we're sunk. This equation is impossible to balance, right? Well, actually, no. It is possible to balance. We're just gonna have to keep going higher and higher and higher. So what I would do in this case is take your lowest coefficient, and in this case, excluding this oxygen, it's here, there's a 1 in front of that butane. And let's make more of it. So instead of 1 butane, let's have 2 butanes. And yes, I know this is gonna throw everything out of balance, but it's just something we have to do to work through this problem to get the right answer. Okay, so 2 times 4 is 8 carbons. And 2 times 10 is 20 hydrogens. Okay, so we need to get 8 carbons over here now. So let's put an 8 in front of that CO2 instead of a 4. And now we have 8 carbons. But we've also messed with our oxygens. 8 times 2 is 16. 16 plus 5 is 21. So now we have 21 oxygens. We still need to balance our hydrogens. So we have 20 in our reactants. We need to have 20 in our products. How many H2Os to get 20? Well, 10 times 2 is going to be 20. So let's replace that 5 with a 10. And now we're going to have 20 hydrogens. Let's recount our oxygens. 8 times 2 is 16. 10 times 1 is 10. 16 plus 10 is 26. And now something magical has happened. My oxygens come in groups of 2s over here in my reactants. And 26 is indeed divisible by 2. So how many groups of 2 do I need to get 26? I'm going to need 13 O2s. So 13 times 2 gives me 26. And now everything's balanced. Now, are all these numbers divisible by a common factor? 13, 2, 8, and 10? No, they're not. 2, 8, and 10 are all divisible by 2, but 13 isn't. So because of that, this is balanced and simplified. 13 oxygens react with 2 butanes to make 8 carbon dioxides and 10 waters. That was a tougher problem, but again, you just kind of stick with it, and then if you get stuck, you can just add more of stuff. You don't need to worry about adding too much, because if, for instance, I went way overboard and ended up with something like 26 O2s, 4 butanes, 16 CO2s, and 20 waters, that's okay, because all of these are divisible by 2, and I could simplify those numbers down to get the actual answer, which is the one we got earlier, 13, 2, 8, and 10. So don't be afraid to kind of play with these numbers, just add things to the reactants, add them to the products, as long as you're willing to look at your final answer and make sure that it's simplified. Okay, that's about as hard as an example can get. I think it's a lot of fun to do these balancing reactions. You're going to do them a lot in chemistry, especially as you move on into all the fun stuff. Stoichiometry, acids, bases, thermochem, all that stuff. I wish you the best. I'll see you next time.